The semiconductor industry has entered a new operating model. As monolithic scaling becomes harder to sustain, performance no longer depends only on making one die bigger and denser. It depends on making multiple dies work together with near seamless efficiency. Marvell has positioned itself at the center of this transition by advancing high-speed connectivity and chiplet-based architectures. Its role is not simply to move data faster, but to make distributed silicon behave like a unified system. In that context, die-to-die interconnects are no longer a technical detail. They are a strategic enabler. A traditional system-on-chip concentrates CPUs, memory controllers, accelerators, and I/O onto a single piece of silicon. That model once delivered scale and simplicity. Now it confronts rising cost, yield risk, thermal pressure, and design complexity. The larger the die, the harder it becomes to manufacture economically and reliably. Chiplets offer a different answer. Instead of forcing every function onto one die, designers split the system into smaller specialized dies, each optimized for a specific role. One chiplet may handle compute, another connectivity, another memory interfacing. The package becomes the system, and the quality of the links between dies becomes a decisive business and performance factor. This is where die-to-die interconnects matter most. They provide the electrical and protocol foundation that allows separate dies to exchange data with low latency, high bandwidth, and controlled power consumption. In practical terms, they let a package communicate as if it were a single chip, preserving the architectural benefits of integration without the penalties of an oversized monolithic design. The challenge is substantial. These links must deliver signal integrity across extremely short distances, support demanding throughput requirements, and remain efficient enough to scale across large systems. They must also fit within packaging constraints and align with broader ecosystem standards so that chiplets from different functions and potentially different vendors can work together. Marvell's contribution is significant because modern infrastructure increasingly depends on exactly this kind of modular design. AI accelerators need dense, high-bandwidth communication between compute elements. Networking silicon must move packets with precision and minimal overhead. Data infrastructure platforms must balance speed, reliability, and power efficiency at scale. In this environment, die-to-die interconnects are not merely an engineering upgrade. They are the bridge between today's scaling limits and tomorrow's heterogeneous systems. They enable the industry to build larger logical systems from smaller physical components, improving flexibility, manufacturing economics, and time to market. The future of advanced semiconductors will not be defined by one giant die replacing all others. It will be defined by how intelligently the pieces connect. Marvell's work in high-speed connectivity and chiplet systems places it on the critical path of that transformation, helping shape the next generation of AI, networking, and data center silicon.